One of the really great things about a velocity time graph is that the area under the graph gives you the displacement. Delta x. And so that area is generally very easy to calculate, and it's a really fast way to avoid using the kinematic equations to calculate delta x because you can just read it simply off of the graph itself. Let's see how that works. Now, when we say the area under the graph, what we mean is the area between the line on the graph and the horizontal axis. So that heavy axis that's running straight through the middle of this graph. And so for the section of time from 30 to 50 seconds, I can see that the area between the line and the horizontal axis is just a triangle. And it's pretty easy to calculate the area of a triangle. It's just 1/2 the base times the height. And so I can very quickly just calculate that. I can go in, and 1/2 base times height is equal to a base. Well, that base is from 30 to 50. And so 50 seconds minus 30 seconds equals 20 seconds. So let me just put that 1/2 in there before I do that. 1/2 times 20 seconds. And my height is going to be 6 meters per second minus 0. So 6 meters per second. And that is going to equal delta x. So that's going to equal 1/2 of 20 times 6 is 120. And my units are the meters per second times the second. That second will divide to 1, and I'm left with 1/2 times 120 meters. And that is just 60 meters. Delta x. Now, occasionally, when you're looking at a VT graph, you're not going to have a perfect triangle or a perfect rectangle. You're going to have some sort of trapezoid type feature, quadrilateral. And so what you can do in that case is you can break the shape of the graph area down into rectangles and triangles, and then you can just calculate the parts and add them together. So for example, from 60 to 90 seconds, I can break that area under the graph, by which I mean the area between the line and the horizontal axis. I can break that down into a big green rectangle that you can see there and a little orange triangle. And then all I need to do is take the area of the rectangle plus the area of the triangle. So the area of the rectangle, that part, is going to be equal to just length times width. Or in this case, I'm going from 90 to 60 seconds. So I have 30 seconds multiplied by, I have negative 3 meters per second. It is very important to maintain the signs, okay? So here I have negative 3 minus 0, and that gives me negative 3. So that means that that rectangular part of the area under the graph is going to be equal to negative 90. My units are meters per second times seconds, which comes out to meters. And now I just need to do the little triangular part. And remember, the triangular part is just 1/2 base times height. So 1/2. My base is still going to be 30 seconds because that continues from 60 to 90. And in this case, the height is just that wee little bit right there. It's actually -1. It's -4 minus -3. So I have -1 there. And 30 times -1 is 30, -30. Divided in half, that is going to be -15. Again, meters per second times seconds is simply meters. To get my total displacement, I just add those together. I have -90 meters plus another -15 meters. So delta x is going to be equal to -105 meters, which means that from 60 seconds to 90 seconds, the object is going to move 105 meters in the negative direction. It's important to watch your signs. I can't emphasize that enough, especially as we go forward and problems get more complicated. So make sure you understand this, and now it's time for you to try it.